Okay, welcome back everyone. Good afternoon. We are in the last talk of section B of the first day of our workshop. So now it's the time for Yuriy Drozd to speak. Yuriy is from Howard University and also from the Institute of Math, NAS of Ukraine, Watertown in US. So, Yuri, welcome. You may speak. Thank you.
Thank you. Thank you very much. Я дуже дякую організаторам цієї чудової конференції за можливість тут виступити. I am very grateful to the organizers of this conference for the opportunity to present here my talk. So now I will start. Thank you. Okay. So my talk is devoted to Bäckström and nodal curves, which is the work in progress of Igor Bourbon. Yeah. And first of all, I will recall some historical things. Yeah, well, first of all, what is nodal curve? Nodal curve means that a kind of algebraic curve that such that all singularities are simple nodes. As in nodal cubic, the simplest example. Yeah, it means that if we take completion of a local ring, then it is isomorphic. I will always suppose that my field is algebraically closed, for instance, C. So it means that the completed local curve is just this one times product of x. Yeah. First of all, something about the role of these curves in the representation theory of coherent sheets and so on. In 1969, Nazarov and Reuter classified all finite modules. Finite means finitely generated over this ring. Yeah. It was a very interesting result, which gave origin to a series of important results for the theory of representations. Then, in 1972, I generalized for non-commutative rings. Not for all rings, for the so-called pure Noetherian. Which means Noetherian without Artinian ideals. Yeah. In 1990, it was 1990. In 1972, I showed that only quotients of this ring and a very small ring modulo x and the y square are of tame representation type. Among commutative rings, of course. In 1972, it was in 1990, it was generalized. I generalized it for non-commutative pure Noetherian rings. It was the first time when nodal rings appeared without this title. Yeah, I didn't give them any title. And in 201, Broil and myself showed that only nodal curves among singular curves of can have same category of coherent rings, of coherent sheaves. And moreover, not all, only of linear or cyclic type, which means that they consist of projective lines which are organized like this or like this. In the here also, of course, if there are only two components, it looks like this, intersection of two quadrics, or if one component that is just a nodal curve. On the other hand, in 1979, Ringen and Roggenkamp introduced a new class of orders, namely so-called Bäckström orders. Bäckström was a PhD student who, in 1972, considered some examples of such orders. Namely, what is a Bäckström order? A Bäckström order is an order A, such that it is contained in a hereditary order. A is contained in hereditary order H. I recall hereditary means that global dimension is 1. All ideals are projective. Yeah. And they have common radical. Okay. They called them Bäckström orders and showed that their representation are in a natural correspondence with representations of so-called valued graphs or valued quivers. Okay. Namely, in this terms, we can say that nodal order is a Bäckström order such that the length of A of tensor product H with any simple A module is at most for any simple A module U. In 204, Bourbon and I considered derived categories of nodal orders. We described them completely. They are tame in the sense of representation theory. And that was the first step to the derived the theory of nodal Bäckström and nodal rings and orders. Then in 211 we considered nodal curves, Bäckström and nodal curves, non-commutative. And we established, derived the whole tilting theory. And it relates them to some good finite dimensional algebra. For instance, example, if we consider the intersection of two quadrats, it's coherent. If this is our curve X, then coherent curve is almost the same as modulus over the algebra A, where A is equivalent relation. I will describe it. We will see why there are different colors. And the relation is that products of fixed color are zero. All products of black, green, red, or yellow, or blue arrows are zero. Yeah, that is a very interesting example. Yeah. Okay, in 212 to 213, Voloshin and I established a tameness criterion for category of coherent sheets over non-commutative curves. Yes. Okay. And at the same time, we okay. Now a bit about classification of such curves. I will consider curves, so I let R be the power series, M be the maximal ideal generated by T. So it was known.
Я теж зайшов на конференцію. Просто хотів сказати, що будь-хто зайти не може. Ти коли заходиш, там той, хто головний, має дати можливість зайти, кнопку натиснути, дозволити.
Sorry. Hereditary. First of all, which are hereditary orders? So I will consider first the local structure, so local rings. Hereditary are very simple. They are just the products of such rings. We consider matrices, block matrices, such that the blocks on the diagonal are all with elements from maximal ideal. All other blocks are arbitrary. Yes. Okay. Now, about nodal. I will first describe so-called basic. Basic means that a modular radical is product of fields. To construct all basic nodal orders, we take a hereditary order, and if we want to construct basic hereditary order such that all blocks are either 1-to-1 and 2-by-2 blocks. Which orders blocks are these blocks are either 1-to-1 or 2-by-2. That's the first step. Then define a symmetric relation. Symmetric and irreflexive. On 1-to-1 blocks. And such that for any block I, there is at most one block J such that I is in this relation, is related to J. Okay. Then consider in this hereditary order H the sub-algebra of matrices satisfying the following condition. First, if the blocks I and J are equivalent, then the ith block is congruent to the jth block modulo M, modulo maximal ideal. So all these diagonal blocks, if they are related, then diagonal blocks are the same. B, if in 2-by-2 blocks, any the process 2-by-2 blocks is congruent to diagonal matrix, the gain modulo M. Now, for instance, I will show an example. Suppose that we have 3-by-3 matrices, and we have here 2-by-2 blocks, then 1-to-1 block, and for instance, we have 1-to-1 matrix, 2-by-2 matrix, and we have only these blocks. It is the first block, the second block, the third block, and the fourth block. We have 4 blocks, and let our relation is just 2 blocks 2 and 3 are. Okay, then we have the following thing. Our ring is the following. Sorry. In 2 by 2 blocks, we must have diagonal matrices. So here we have anything or anything. Here outside we must have elements of maximal ideal. Then under the diagonal Rm, as in our hereditary case, as here. Yeah. Then these two blocks are equal modulo R. So A is congruent to B modulo M. And that's all. Here we have anything. So this is, you see, due to this relation, this ring is indecomposable. Yeah, we took a product of hereditary rings, 3 by 3 and 2 by 2. But the resultant ring is indecomposable. Okay. It gives us all nodal curves. Okay. Now we are looking for a real case, and we have already the result, but it is not very organized. Okay. One more important thing related to this is the so-called group action. I recall that let G, a group G, acts on a ring A. It means that every sigma in G is related to an automorphism of A, which maps A to A sigma, so that for any sigma and tau from G, the result of action of A, if we act sigma and then tau, it is not necessarily the same as the action of product, but it is always like this. This automorphism, this one, and this one are just different by inner automorphism. Certainly, this lambda must satisfy some well-known relations. I will reproduce it here. One can see it, for instance, in the book of Jacobson, Theory of Rings, or in any other book also, in many books. Yeah. Then we have so-called crossed product. It is the set of formal linear combination like this, finite, of course. Yeah. And the product is defined like this. If we multiply the sums, then A is multiplied by B times sigma, and then not sigma tau, but up to lambda. Yeah, this is again well-known definition of cross product. Yeah, and certainly, yeah, such rings appear very naturally in the theory of both in theory of orders. Also, they all appear in the so-called mirror symmetry. for instance, in a paper of Lekeli and Polishuk, so-called static curves. They consider so-called static curves, which pair the action of cyclic groups just on these curves. Non-trivial action. Yeah. And the main result here is the following theory. Suppose that A is hereditary or Bäckström or nodal, and G is finite, and its order is invertible in A. As they say, Maschke case. Then the cross product is also respectively hereditary or Bäckström or not. Oh, I say I have several minutes. I can explain one important thing. These things is rather simple. Not complicated. Not simple is to it follows from a general theorem that if we consider the category of AG modulus, it is equivalent to the following thing. We must take the category of A modulus. Then there is a natural action of G here, so we can take a cross product with G and take a so-called additive closure or Karubian closure, which means that the smallest category, which containing this one, and closed under direct sums and sums. So then it is necessary because the category of modulus is additive and then even Karubian or added product space, but this category is not, can be not. Usually it is not. Okay. So it gives us the theorem for hereditary and Bäckström orders. For nodal, it is not so simple. Yeah, because okay. But then we use the following combinatorial lemma. It consists of two things. If okay, no. It is the following. Suppose that A is Bäckström, H is the endomorphism ring of its radical. So the name AH is just Bäckström pair. Then, first, if H has two generators as A module, then A is nodal. And second, if A is basic and nodal, then H has two generators as A. Okay, if A is not basic, it is not necessary so. Important that it is basic. Then we have the following proof. Of theorem from this lemma. Take A nodal. It is Morita equivalent to a basic nodal B, and it B is contained in hereditary like there, and H has two generators of a B. Then, of course, it is very easy. First of all, H or G is also hereditary, and it has two generators as B of G. They're the same generators. Yeah. Then, by lemma, BG is nodal. It is not more basic. It is not basic. But here we do not need that it is basic. Okay, it is nodal, and it is one can prove it is Morita equivalent to A and G. Then we have that AG is also nodal. That was a question for several years, whether the cross product of nodal ring with a finite group is again nodal, but now we have it. Okay, I think I will stop right now because my time is almost over. And thank you very much.
Thank you, Yuriy. Thank you very much.